Okay. So jumping into it, NMR works on the principle that nuclei have spin. So just like electrons have spin, the technique that we use to look at electron spin is EPR, electron paramagnetic resonance. I think somebody might have already chosen that for their topic, Caroline. Okay. So EPR is sort of the electron version of NMR that looks at electron spins, while NMR looks at nuclear spins. Now, nuclear spins, there are lots of options. The spin for a nucleus is given the symbol I. And depending on what you have in your nucleus, I has different rules. And so I could be 0 if the number of protons is even and the number of neutrons is even. No spin doesn't help us out a whole lot. There's nobody that does NMR on these kinds of molecules, right? You're not going to find anybody that does neon 20 NMR. Doesn't do anything. That's also why we don't use carbon 12 NMR, right? All the carbon NMR that we do is carbon 13 NMR. I could equal half integer spins, so 1/2, 3/2, 5/2, etc. If either number of protons or the number of neutrons is odd. The other one has to be even. So another way of thinking about that is that the number of protons plus neutrons is odd. Then the last option is whole integer spins, and so I can equal 1, 2, 3, etc. if both the number of protons and the number of neutrons is odd. So we have an even number of nucleons, but both protons and neutrons are odd. Most generally, and this is not, usually the nuclei that we're interested in have half integer spins. And so in this table here, all of these have half integer. And, these 4 are by far the most common 4 nuclei that you're going to look at. There, you can build NMR probes to look at special things. I worked with a lady who did her PhD at Emory, and they were interested in tungsten complexes, sort of an inorganic problem. And they had Agilent, an instrument manufacturer, build them a custom tungsten probe that was built for whichever spin tungsten is. I don't know which isotope they were looking at, but you can build an NMR probe for almost any element as long as it doesn't have a spin of 0. Based on this nuclear spin, right? This is like an inherent spin. The quantum number for that spin is m. So just like m that we use in electrons, right? We're using m for nuclei. And so m is equal to I minus 1, ... negative I. And so a couple things to keep in mind. This is a lot like our M sub L value, right? When we talk about electron quantum numbers, in terms of how we figure it out. If there's no magnetic field, so in the absence of a magnetic field, if I write B, do you all know B is magnetic field? Did you use B in physics? Yes, excellent. So we're going to use B naught as magnetic field. All of these quantum states, right? So all the values of M have degenerate energies. What does degenerate mean again?
Same energy.
They're all the same. Yeah, absolutely. So degenerate energy means that all of those values of M have exactly the same energy. So for these four nuclei, if I is 1/2, what are the possible values for M?
One half and negative 1/2.
That's it. So we have +1/2 and -1/2. Again, very similar to electrons, right? It's going to look very similar for us. And so these two spins, M +1/2, M -1/2, same energy level as long as we don't put them inside a magnetic field. But what do we do with NMR? Man, we put them in magnetic fields. This little table that I have here with these gamma values, let me change colors.
That was a quick question.
Go ahead.
How'd you, so I know if you do I -1, so the 1/2 -1, that's -1 or -1/2. How'd you get the +1/2?
So that's our I, right? If I is 1/2, then that's a possible value. So for all four of those nuclei, I is equal to 1/2. And so that's our first value of M. And then I -1 is equal to -I, and so that's our only other value for M.
Gotcha. Okay.
All right, so these gamma values here, these are called the gyromagnetic ratio. You can also call it the magnetogyric ratio. Both of these are used in the literature. It sounds like a real made-up word. But it's the ratio between the magnetic field of the nucleus and the angular momentum, or the spin of that nucleus. That's what that ratio is. And so mu, magnetic field of the nucleus, is equal to gamma times p, the angular momentum. So nuclear I'm missing a unit. The unit on angular momentum should be radians per second. And so this should be, radian per second times 1/Tesla, so that all your units cancel. Sorry about that. The reason I left it off is because we often convert angular frequency, angular momentum, angular frequency to linear momentum, and that radian just kind of poof, goes away because there are 2 pi radians in a circle, and so when we divide by 2 pi, we don't usually add a unit to it. We don't usually pop on that 2 pi radians, and so think of the radians as being an optional unit. Okay. All right, so these spin states, as we sort of go through and we put our sample in a magnetic field, right? That's what we do with an NMR. These energy states split, these 2 nuclear spin states split. +1/2 is lower in energy, -1/2 is higher in energy. And +1/2 just means that it's aligned with the external magnetic field. Right? So this lower energy dude is aligned with the external B0. I switch between all capital writing and sort of normal case writing, and it makes me sometimes wonder if I'm really a serial killer. You know how they say like your handwriting tells a lot about you, but I switch it so much. I don't know what that says. Anyway, this one up here is against B0. Okay. When we look at the energy of a transition, at the energy of one of these spin states, I'm going to go ahead and convert it to linear frequency, or I'm going to build that in. Our textbook goes through the whole kit and caboodle, but I'm going to go ahead and build in that conversion here. So the energy of any of these spin states is equal to negative gamma times that m, that quantum number, times h, our Planck's constant, times whatever that magnetic field is, B0, divided by 2 pi. But rarely are we interested in the absolute energy of a single level. More often, we're interested in that transition between the two, right? And you could do E minus E plus, right? If we're looking for that gap between the -1/2 and the +1/2. But when you do that, we get delta E, and I'll go ahead and give it to you. The negative drops out. Also, the M drops out, because when we subtract these two, we have a half. We have a -1/2 minus a half, and the negative out front all cancels out, and we get rid of our M as well, right? And so we just end up with gamma H V0 on 2 pi. And so that's this energy difference. With any energy, we can convert that to a frequency. And so the frequency that we're going to use, it has a naught there. So nu naught is equal to gamma, if we just rearrange this, gamma times B0 divided by 2 pi. Okay. Since E equals H times nu, if we just rearrange things, we get nu. The H and then delta E drop out. This guy here is called the Larmor frequency. So I'm going to carry him over to the next page. A few things to keep in mind about this Larmor frequency. The first is that this is how we describe the sort of power, the size of an instrument. When you hear somebody talking about an NMR, you talk about, oh yeah, it's a 400 megahertz NMR. 400 megahertz is this Larmor frequency. A caveat there, it's only for the proton frequency. Right? And so because each of these nuclei have different values for gamma, you're going to get different frequencies for each nucleus. And so when we describe an NMR instrument, the frequency that we use to describe it is the Larmor frequency for the proton. The NMR that we have at Wofford is a benchtop NMR. I don't know how many of you have seen it in that little skinny room next to the organic lab. It's a 60 megahertz NMR. That's kind of small, but it's okay. So it's a 60 megahertz. Mega is times 10 to the
6.
There we go. So 60 times 10 to the 6th hertz is equal to, well, we need to figure out gamma for hydrogen. That's easy enough. It's on our table. 2.6752 times 10 to the 8th Tesla, inverse Tesla, inverse second. I've also seen this written as hertz per Tesla. Right? If you want to write it that way, by all means. B naught, I don't know, divided by 2 pi. So what's B naught for the instrument we have in RMSC 335?
.4 Teslas.
Yep. 1.4 Tesla, right? So this is kind of a wimpy magnet in the NMR world, right? The biggest NMR that I know of has a magnet of about 28 Tesla. So, 20 times this. In terms of other magnets that we are familiar with, perhaps the Earth, for example, has a magnetic field. It's a tiny one. The Earth's magnetic field is about 40 micro Tesla, right? And so relative to the Earth's magnetic field, golly, this is huge. But the Earth doesn't really split nuclei into different spin states either. So B naught, 1.4 Tesla for a 60 megahertz instrument. That will always be true, right? Because when we say the frequency of an NMR instrument, we're always talking about that proton frequency. They could have just as easily, when they started manufacturing NMR, put the size of the magnet and said this is a 7.1 Tesla, but they just didn't do that. Why? I don't know, because nobody really knows what 600 megahertz means in terms of resolution any more than they know what 12.5 Tesla means in terms of resolution. Bigger number, better resolution, period. We'll talk about why in just a minute. So this is some practice. Go ahead. These are two big NMR, 600 and 800 megahertz. The bigger magnetic fields are usually used for carbon NMR. If you look at that table that we had of the gyromagnetic ratios, carbon is by far the smallest of those four. And so we need a bigger magnet to get similar resolution for carbon as we get for, as we get for hydrogen proton NMR. Did you get similar numbers? Excellent. I have a little anecdote to tell you. Purdue has an 800 megahertz NMR. It's in the basement of the building. And what they did is they dug a hole next to the building, broke down the basement wall, moved the instrument in, and then rebuilt the basement wall. That's the only way to get an instrument of this size into the building. I mean, you can tell how big it is, right? This is a flight of stairs up to the top of the instrument. And so the magnet is so powerful. And you know, these are big cylinders, and a magnetic field, if your magnet's oriented this way, your magnetic field lines go up and around, right? There's in the lab directly above that instrument, there's a line on the floor that marked out the magnetic field. And if you stepped into that line, you know, the magnetic field was strong enough that like your credit cards could get wiped. You know, it could interfere with your watch or your cell phone or stuff like that. So these are pretty powerful magnets. There's a story, I don't know how true it is, that at the University of Michigan, they had a very early NMR. There was a high field NMR like this with a strong magnetic field that wasn't shielded very well. And it was in the corner of a building. And as they were outside mowing the grass, the guy on the lawnmower just kept drifting toward the building in that corner. So I don't know if the story is true or not, but if you go on Google Maps and you look at that corner of this building, there is like a circle around the corner that's not grass. It's like rocks, like so they don't have to mow it. So true, not true, I don't know. Pretty awesome.
Where is that?
At Michigan State. Yeah. So a friend of mine from grad school went to Michigan State and told me that story. Again, I don't know if it's legend or if that's just, or if it's a true story, but there it is. Okay. So how do we get NMR signal, right? What's actually happening for us to get this signal?
Will you explain the second part of the last slide?
Sure.
The 201 megahertz?
This one?
Yes.
So I plug it back into that same equation. I use my, so it says for the 800 megahertz instrument, which is this higher Tesla, I plug that in here. Since I'm looking for carbon, I use carbon's gamma there, and I find my frequency. Did you get something very different?
We're good now. We were a
But
little confused.
Why wouldn't you use the carbon? Like, why wouldn't you do that calculation again, but with the carbon number?
So,
To find B.
so the instrument magnetic field doesn't change, right? So when we talk about a NMR instrument, this says 800 on the side of it, right? That 800 is the frequency of just hydrogen. That's just sort of how they market it, because proton NMR is the most common NMR. The size of that magnetic field, they're not changing that enormous magnet to do a different nucleus, right? The other thing that changes is the frequency at which it's resonant.
Okay.
Right? So the energy gap is different. If I put carbon in that magnet, the energy gap is different than if I put hydrogen in that magnet.
Yeah.
So the nuclei are different. They behave differently in the same magnetic field. That's why I said I think it's a little dumb that they market it this way. If you told everybody, hey, this is an 18.8 Tesla NMR, it would be easier to explain exactly what's going on. Okay. All right. So, what's happening when we put something in an NMR? First, in this image, right, this big arrow, this is our B naught. Oops. So this is the applied magnetic field. And then all of these are supposed to represent the nuclei. And so when we put our sample in an NMR, we're going to, what's going to happen is before we put our sample in, all those spins are oriented in golly gee any kind of direction, right? Those spins are randomized, again, because the magnetic field of the Earth is not strong enough to line them up. Those magnetic field direction of those nuclei are any which way. As soon as we put them in a magnetic field, they're going to either align with the magnetic field or align against the magnetic field. And most of them align with a magnetic field. So this is showing 10 little arrows, and 6 of those 10 arrows are aligned with the magnetic field, right? This is very generous. You would get amazing resolution if 40% of your nuclei were in the excited state. Really, it's on the order of parts per million that we have nuclei in the excited state, right? Not 40%. Ashley, maybe this explains a bit more to your and Annabelle's question. If we increase our Tesla size, the magnetic field strength here, we have this larger energy gap for, this is for protons, but it would look similar for carbon. If we drew carbon sort of on top of this, would carbon have a wider gap or a smaller gap?
Smaller because the gamma is smaller.
Yeah, so smaller because gamma is smaller, and in the last example, it was 800 megahertz for proton and only 200 megahertz for carbon, right? And so if we were to draw in carbon, right, it might look something like this. 1 plus over half. That doesn't work. Right? And carbon, the gamma for carbon is about a quarter of what it is for hydrogen. We saw that it went from 800 to 201, right? That's about a quarter. And so that's a sort of a good estimate, right? So here, this 400 would be about 100. This 200 would be about 50, right? I know maybe you can't see that, but it's about, a quarter of the frequency. Right? So, in any case, we have these different magnetic field directions, and the way that we sort of determine how much signal we're going to get is by how many of those nuclei are in the excited state, right? So the more nuclei that are in the m equals negative a half state, we're going to get better signal. Which is why we care about this energy gap. So we use Boltzmann distribution for this. And so let's see, I'm going to make sure our textbook uses the same. They used NE over NG when we talk about AA. I want to make sure they use the same. I just want to match their terminology here. Let's see. In this chapter, it looks like they're just using N2 over N1. So that's what I'll do. N2 over N1 equals G2 over G1 e to the negative delta E over KT. Now, we know by now that we have a different way of writing delta E for this nuclear system. And so, again, we assume that these degeneracies are 1. So that sort of falls out. But if we substitute in what we know is delta E, then we end up with this ratio N2 over N1 is equal to E to the negative gamma H B naught divided by 2 pi KT. Okay. So from a few slides previous, we know that delta E is equal to gamma HB on 2 pi. And so if we look here, the stronger our magnetic field, the more of those nuclei we're going to have in that excited state. Of all of these, the only two that we really have any control over are the magnetic field and the temperature. And so the magnetic field, get it as high as possible as sort of a side benefit to have very high to have very high field magnets. They have to be super cooled, and so they're cooled with liquid helium. The liquid helium is actually kept cold by a jacket of liquid nitrogen, so your helium doesn't go away too quickly. And so the inside of this magnet is pretty chilly. And so, we're at relatively low temperatures as sort of a side effect of being at very high field strength. So that's a cool thing about it. Okay, let's do a Boltzmann distribution problem here. We have a nucleus, proton nucleus, in a 4.69 Tesla magnetic field. Calculate the relative number of nuclei in the ground state if 10 to the 6 of a million are in the excited state. Golly, I feel like I have that wording back. Where it is. Oh no, yeah, okay, that's right. I'll give you a temperature here. Let's say it's at 100 Kelvin. Oops. I put my million in the wrong place. If you're copying me, my million is the excited state, not the ground state.
Dr. Davis, where did you figure out that K value? The
This?
1.38.
Yeah,
Yes, sir.
that's Boltzmann's constant.
Oh, okay.
What does it mean by relative number of nuclei? Like, does it want that ratio that we get, or does it want how many, the difference?
So it's only relative because there's surely way more than 1 million in our sample, right?
Yeah.
And so we're just comparing it to 1 million because we talk about this difference in terms of parts per million. Okay. So what did you get for M1?
Got 10,958,000.
You're off by a factor of 10 somewhere. It should
It
be
might just be
1,096,000. That's okay. Should be
No, I'm off by
1,096,000. Did anybody else get that? Yes, no, maybe? Ashley got a thumbs up. Okay. So we say this is a 96 ppm excess. Right. Right. And so out of, we have 1 million nuclei, and we can only excite, for the way that the quantum world works, we can't have more nuclei in the excited state than in the ground state, right? Because as soon as there's more in the excited state, they'll start relaxing back down, right? And so we can never have more in the excited state than in the ground state. And so the most that we can excite from one state to another is, half of that difference. That's why it gets funny because, this is, we can only excite half of that number up to the excited state. So if we have a 96 ppm excess, really we can only excite 45 nuclei out of every million to the excited state, right? 48 nuclei. Okay. As I was doing this problem, I think I may have worded a previous slide funny. This more nuclei in the M negative a half state, the better the signal. Right? That's the more nuclei we can move up there, right? That can be excited. So when we're down here at low field at 2.34 Tesla, we have 100 megahertz separating it. That's a relatively low energy gap. And those two states are going to be pretty evenly populated, right? As we change this energy gap, it's going to be harder for those nuclei to sort of end up in that excited state. And so the ppm excess that you have in the ground state gets bigger and bigger and bigger as you go to higher and higher magnetic fields. And so we did 4.69 Tesla. So 4.69 Tesla has a 96 ppm excess. Just so you know, a 28 Tesla magnet under the same conditions would have almost 600 ppm, right? And so you have a factor of 6 difference, right? That comes from the fact that the magnet is 6 times stronger. But you have a factor of 6 difference in the amount of nuclei that you can excite. And so you can have a resolution that's 6 times greater. Right? So we talk about signal noise and all that. Increasing magnetic strength is one of the main ways that we can do that. All right, we'll call it good there. And remember, sleep in on Friday. Ta-ta.
See you, Dr. Davis.
Bye. Thank you.